Thus far, we've looked at a little bit of electric motor dynamics. We've covered incremental motion and velocity profiles and gearing. So in this video, we'll look at the effects of gearing on the motor dynamics and whenever we have incremental motion. First of all, let me begin with an example system. Here is our gear pair. We've got the input gear and the output gear, so N1 and N2, the number of teeth on the gears, and our input shaft, where we have the torque tau 1, and this is a function of time. The displacement of this shaft is theta 1, and on the output shaft we have some loading. We've got a moment of inertia, J, and we have a torsional spring, stiffness K, and viscous damping, C. The spring opposes the output shaft displacement, which is theta 2, with a force proportional to the displacement, and the damper viscous damping opposes motion with a force proportional to the velocity, theta 2 dot. Now we want to apply Newton's second law. But before we do that, let me mention that though there are two variables here representing displacement, theta 1 and theta 2, there is only one independent motion. That means that if we held the output shaft fixed, we would not be able to turn the input shaft. And vice versa. If we held the input shaft, then we couldn't turn the output shaft. So the relationship between theta 1 and theta 2 is just that theta 1 is proportional to theta 2. And what we want is a differential equation relating the torque tau 1, the input torque, and the displacement, the output displacement. Or, since these two displacements are proportional, the input displacement. But we want a differential equation relating torque to displacement. So let's generate the equation of motion by using Newton's second law on the on shaft 2. Or the output shaft. The torque applied to this shaft is N2 over N1 times tau 1, because the gear ratio magnifies the torque, and that's a function of time. Now, if the shaft rotates in the positive direction, then we're going to have a force from the spring, so minus K times theta 2, and we'll also have a force from the damper, C times theta 2 dot. And all those forces are equal to the product of J and theta 2 double dot. Now we can use the relationships that we learned from the gear ratio, where we have that tau 1 over tau 2 is N1 over N2. Well, we already used that one. So tau 2 is equal to tau 1 times N2 over N1. And also theta 1 over theta 2 is equal to N2 over N1. So this gives us that theta 2 is N1 over N2 times theta 1. The reason we're going to use that is because we want to find an equivalent system here, where we just have the system as seen by the load on the input shaft. So now let's substitute in for theta 2, and we get that N2 over N1 times tau 1 of t minus K times N1 over N2 times theta 1 minus C times N1 over N2 times theta 1 dot is equal to J times N1 over N2 times theta 1 double dot. That just used the substitution for theta 2. And we can rearrange and multiply by this ratio to get our differential equation. So we have J times N1 over N2 squared times theta 1 double dot plus C times the same factor N1 over N2 squared times theta 1 dot plus K times N1 over N2 squared times theta 1, and that's all equal to our torque tau 1 of T. And we can see from this equation that this system up here with the impedances attached to the output shaft is equivalent to the system depicted here, where we have N1 over N2 squared J. That's our equivalent moment of inertia. And N1 over N2 squared K is our equivalent torsional spring. And what's our equivalent damping? And this is all on shaft 1, so theta 1 is the displacement. This term here, or this process of making an equivalent system on a different shaft, where we have impedances, they're called, on one shaft on one side of a gear pair, and we want to find an equivalent system on the other side of the gear pair. That process is called reflection. For example, we could talk about reflected inertia or reflected damping. And this reflection parameter that we see, in order to reflect an impedance from one shaft or from one side of a gear pair to another, is given by the number of teeth on the destination shaft, where you're moving your moment of inertia to, divided by the number of teeth on the source shaft. And this quotient is squared. So we see here we had a moment of inertia on shaft 2 and we moved it to shaft 1 down here, and it's reflected, that moment of inertia is reflected by the value N1 over N2 squared. So N1 is our destination shaft, and N1 is the destination shaft, and N2 is the source shaft, because it moved to shaft 1 from shaft 2. This parameter is used to get an equivalent inertia, etc., on a destination shaft. Now, we're going to apply this concept to an electric motor. As we know, electric motors often have gearing in applications, and so we're going to look at the effects on the motor dynamics and also go through an example of incremental motion. Here is an example system. We have our motor on the input shaft of the gear pair. The armature has some moment of inertia, JA, and there's damping associated with the armature, C sub A. So here we have the motor torque and the motor shaft displacement. And N1 is the number of teeth on gear 1, and N2 is the number of teeth on the output shaft. And we have a load, moment of inertia, spring, and damping, JL, KL, and CL. So let's examine the equation of motion. We're going to look at shaft 1. So we have the moment of inertia, JA, plus the reflected moment of inertia due to the load. And it's the number of teeth on the destination shaft, so that's N1, divided by the number of teeth on the source shaft, N2, because we're going to shaft 1 from shaft 2. And that ratio is squared, and that is our reflection parameter for J sub L. So there is the equivalent moment of inertia, like you can see in this figure. What we're doing is finding the equivalent system that the motor sees. The motor could tell no difference between a system with a gear train and this system here where we just have one shaft and the equivalent impedances, equivalent moment of inertia, equivalent spring, equivalent damping. And our equivalent moment of inertia is JA plus the reflected JL and theta M double dot. Now we have the equivalent damping, CA plus reflected load damping, N1 over N2 squared times C sub L, and that gets multiplied by theta M dot. And then finally there's no spring on the motor shaft, so we just have the reflected load spring. And that's all equal to the motor torque. So we're typically interested in the load output. Therefore, we're going to substitute theta M is N2 over N1 times theta L. And doing this, we get the following expression. We have N2 over N1 squared times JA plus JL theta L double dot plus N2 over N1 squared CA plus CL times theta L dot plus KL times theta L. Oh, this up here should be KL. KL times theta L. And that's all equal to the torque on shaft 2. So N2 over N1 times tau sub M. And this equation came directly from this one, just making this substitution. And it works out to be this. So you can see here the differential equation if we're interested in the displacement of the motor shaft, or the differential equation if we're interested in the displacement of the load shaft. You can see the difference is that for the motor shaft we're reflecting the load impedances, and for the load shaft we're reflecting the motor impedances, JA and CA. And also the motor torque is magnified by the gear ratio. Let's look at an example of incremental motion. Okay, again we have a gear pair. Here N1 is 40, and these are non-ideal gears, so we have J1 is equal to 1, and we're not going to bother working with units on this one. Here's our motor, and it has armature moment of inertia of 0.5. So we have our motor shaft displacement, theta M, and the output gear has a number of teeth, 400, so the gear ratio is 10. And on that shaft we have a load moment of inertia, JL, and JL is equal to 60. So this is the displacement, theta L. And what we want to do is find the differential, first of all, the differential equation, relating the load displacement to the motor torque. And secondly, the motor torque required for an incremental motion of 2 pi radians, so 1 revolution in half a second. And that's using equal time trapezoidal velocity profile. So part A, we want to find the displacement of the load shaft. So we're going to reflect the input shaft inertias. I say inertias because on this shaft there are two inertias. There's an inertia from the armature and an inertia from the gear. So we want to reflect both those inertias to the output shaft. And also the torque is magnified. All right, here is our differential equation. We're reflecting to the load shaft from the input shaft, or the motor shaft. So that's N2 over N1 squared is our reflection parameter. And the moments of inertia that we're reflecting are JA and J1. And adding to that, we have, J2, this gear has a moment of inertia, and it's equal to 3. So we're adding J2 and JL. Theta L double dot, and that's equal to the torque on shaft 2, which is N2 over N1 times tau M, which is a function of time. So we get 100, since that's N2 over N1 squared, 100 times 1.5, which is JA plus J1, plus J2 plus JL, which is 63, times theta L double dot, is equal to 10 tau M time. And so we get for our final differential equation 21.3 theta L double dot is equal to the motor torque. It's a function of time. So there's no damping in this example. An undamped system. Now for part B, we want to get the motor torque required. So our first step is going to be find the desired motor shaft displacement. And then we're going to reflect the load shaft inertias. We have that the desired motor shaft displacement, theta MD, is equal to the gear ratio N2 over N1 times theta L desired. So we have 400 over 40 times 2 pi, which is going to give us 20 pi radians. And since we're using an equal time trapezoidal velocity profile, we know that the maximum motor shaft speed is 3 times theta md divided by 2 times tc, which is 3 times 20 pi divided by 2 times 1/2 a second. And so that gives us 60 pi radians per second. If we want to find the torque, we need to find the acceleration and then apply Newton's second law. So the acceleration is the change in speed. We go from stop up to omega m max divided by the change in time. Change in speed, omega m max, and change in time is just tc over 3, since we're using an equal time trapezoidal velocity profile, which is 60 pi divided by 1 over 6. And that gives us an acceleration of 360 pi radians per second squared. And again, what the plot of motor shaft speed versus time looks like is this. Might not be to scale, but we have 60 pi is this height here, so 60 pi. Hopefully that's legible. 60 pi is the maximum velocity, And 1/3 of our TC is 1/6 of a second, and then 1/3 of a second, and then finally 1/2 of a second. That's our velocity profile. We start at rest, go up to 60 pi radians per second, continue that for 1/6 of a second, and then go back down to rest. So the motor torque, tau m1 is equal to the equivalent moment of inertia on the motor shaft times the acceleration. So that is JA plus J1 plus, now we need to reflect the load shaft moments of inertia. The destination teeth is N1, the source teeth is N2, square that quotient, and then multiply that by the sum of J2 and JL. And there's our equivalent moment of inertia on the motor shaft. Our acceleration we found was 360 pi radians per second squared. And so we have 1.5 plus, let me see if I can write this. Okay, 1.5 plus, this is 1/10 squared, so 1/100th, 0.01 times, this is going to be 63. And multiply that by 360 pi, we end up with 107 is the torque required for this acceleration phase. And in this video, we looked at the effect of the gear ratio and the term called reflection on the motor dynamics during incremental motion.